Hello everyone. We need to wrap up core 4 here and tackle topic 4. So it says carbon dioxide and water vapor are the most significant greenhouse gases. Other gases include methane and nitrogen oxides, but they have less impact. The impact of the gas depends on its ability to absorb long wave radiation. These molecules hold the long wave or infrared radiation in. This is heat, as well as its concentration in the atmosphere. The warmed Earth emits longer wavelength radiation, heat, and so this heat is then held in by these molecules. And it says longer wave radiation is absorbed by greenhouse gases that retain the heat in the atmosphere. Thus, we refer to this as global climate change, global warming, because when you increase the temperature of the atmosphere, that changes weather patterns. When you change weather patterns, that's the definition of climate. Climate is the combination of temperature and precipitation. All right, so first thing we need to tackle is what we used to call this in the 1990s, early 2000s. We used to call this is question 4A, of course. Okay, we used to call this the greenhouse effect. And this is an antiquated term now because people don't know what greenhouses are. So we're now referring to it as either global climate change or global warming. Again, climate is a combination of temperature and precipitation. So in order to explain why we call it, or used to call it, the greenhouse effect, we need to talk about a greenhouse and your cars, as a matter of fact. So, sun. Sun emits many different wavelengths of energy, and one of those wavelengths is infrared. And the infrared we sense as heat. And you've experienced this. Even on a cloudy day, you get out of your car. So here's car, right? Nice car, look at that. So what happens then is the sun emits many different forms of radiation. One of them is infrared radiation or infrared energy. So if you think of the electromagnetic spectrum, how the visual light is Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. So you have red on the left and violet on the right. So if you go beyond the red, okay, the longer wavelengths of red are therefore your infrared. You take red light and you stretch the wavelength, you get a longer wavelength, and you get infrared. So what happens is glass lets this infrared energy through. So the infrared energy goes into your car. But then what the glass does is it doesn't let that infrared energy back out. So this is why it doesn't even have to be a sunny day, right? You get into a car that's been closed up for an hour or two, and the inside of the car is much warmer than the ambient temperature outside. That's infrared energy. That is exactly how carbon dioxide and methane and NO molecules hold the energy in. So in places that are colder than our environment here in California, they would build these small rooms out of glass. And so they would put in metal framing or wood framing, I suppose. And then they would put glass in the panes like such. And the whole idea was to let the sunlight in and then capture it just like it does in the car. And again, this is infrared energy. Well then, just like the glass of the windshield, the energy would be trapped inside of this glass house. And so what people would do is, even though it's snowing outside, the inside of this glass house would be very warm. No fire to heat it, no heaters, okay? You're using sunlight and you're trapping it. So you would then be able to grow plants 365 days a year, even when there's snow and ice on the outside. It's warm on the inside. So then these plants are growing in this glass house. So when you would walk up to it, because of all the plants on the inside, it is a greenhouse. And this is what greenhouses are. Botanists, people who study and grow plants, have greenhouses. And it's a really nice way to keep the plants warm without having to pay for it. You just build a glass house. So this is why we then call the CO2 and the methane greenhouse gases, because they do the same thing. They trap infrared energy. So if you have the Earth and you have the atmosphere surrounding the Earth, composed of many different gases, nitrogen being the most common, but it is inert. And so, hey, guess what? Infrared energy comes out of the sun. Infrared energy. Infrared energy comes out of the sun, penetrates the atmosphere, but then you get your greenhouse gases. You get your CO2, your methane, CH4, and what are referred to as your NOx gases, NO, NO2, NO3. And so people refer to them as NOx. You will hear chemists and researchers refer to these gases as their NOx gases. These all trap this infrared energy, okay? So the energy that then hits the Earth tries to bounce back out and is then held in the atmosphere. Well, if you retain this energy, what happens to your global temperature? Your global temperature increases. You get a global temperature increase. Thus, we refer to the gases that cause this global temperature increase. We call these greenhouse gases. And these greenhouse gases cause the greenhouse effect. Of course, now we refer to them as global climate change gases, but we need to make a list. Greenhouse gases. CO2, CH4, methane, and then your NOx, NO1, NO2, NO3. So since that number can change, we just put an X, and so these are your NOx gases. Okay? So now we need to talk about graphs, because the concentration of greenhouse gases, these guys right here, these are the same thing. The concentration of greenhouse gases have dramatically, this is not a subtle change, this is not a slow change either. They have dramatically increased since the 1900s, the early 1900s. Right about the time of the Industrial Revolution. What do you know? And you say, hold it. How do we know what the atmospheric conditions were 100, 120 years ago? Easy. When ice forms, it forms a crystal lattice, like such. And when the ice crystals form, it traps air on the inside. This is why ice floats. When you freeze water, you ever notice how ice floats? Ice is less dense than liquid water. Why? Because when the ice forms, the crystal lattice traps this little micro bubble of air. Okay? That makes the ice less dense. Well, you then drill into the ice cores at either pole, the North or the South Pole, and you get what are called ice core samples. We know the rate that this ice forms. It's extremely regular because it's based on the path of the Earth around the sun. And so these ice core samples provide data of the atmospheric gas concentrations. And you can go back literally a couple million years. You have to drill down about a mile, okay? It's a tremendous undertaking, but when you then take this ice and you melt it, the sample that comes out is the actual atmospheric sample from when that ice is formed. It's really cool. You then take that ice, put it in a vacuum, and suck out all of the modern atmosphere, and you do some real high-tech science. You wait for that ice to melt. And when that ice melts, it releases its air sample, and then you run mass spectrometry on it and determine what's in the atmosphere sample. We know exactly what the atmosphere was like back accurately 1 million years. It's amazing. How? Because of ice. These are ice core samples. So this is question 4A. You need to be comfortable with the greenhouse effect, and global warming and global climate change are all the same thing. So then, all right, if these gases are so detrimental to the modern ecosystem, we need to talk about sources of greenhouse gases. Where do they come from, right? Well, CO2. CO2 is by far the most common greenhouse gas. Everybody's talking about CO2 now, but as you now know, it's not the only greenhouse gas. So where does this come from? This comes from the combustion of fossil fuels. We call fossil fuels because this is the fossilized plant material from the Carboniferous period. You have an earlier question about peat and peat moss. And so when this plant material, this moss, fossilized, it trapped the CO2 from the carbohydrates in the plant material. All we're doing is we're digging those molecules out of the ground and burning them and releasing the CO2 into the atmosphere. Now, methane and your NOx gases, not as common in the press, in the media, but still equally as important scientifically. These are produced by agriculture, farming. One of the biggest offenders is the beef industry. Cows produce tremendous amounts of methane. We are growing and harvesting so many cows. That's the smell around a cow farm, by the way, that the output of methane by the cows is enough to impact our global atmosphere. It's really impressive. Also, over in Russia, in Siberia, there's this material called permafrost. Now, we used to call permafrost because it was permanently frozen. Okay? Permanently frozen water in a part of Russia called Siberia, if I can spell it properly. There we go. Right? And permafrost is really, really concentrated with methane. Well, we used to call this permafrost because it was so cold it would stay permanently frozen. Hey, well, guess what? Global temperatures are increasing. So the permafrost isn't perma anymore, right? So as the temperature increases, this melts the permafrost. Well, when you melt permafrost, what gas is highly concentrated in the permafrost? Methane. Well, methane, by definition, is a greenhouse gas. Greenhouse gases are called greenhouse gases because they cause an increase in global temperature. Well, you increase global temperature and that melts more permafrost. This is called a positive feedback loop, not because it's a good idea, okay? Because it's like a rock rolling downhill. The farther the rock rolls, the faster it goes, which causes it to roll farther, which means it rolls faster. And so this feeds on itself. It's called a positive feedback loop. This is a positive feedback loop. The methane feeds back or returns into the loop and increases the process, which forms more product, which increases the product, which just more and more and more. This gets to be a runaway train. right? And so all of this discussion about getting warmer and getting warmer and getting warmer, you say, who cares? So it's warmer. I'll just wear shorts, right? Shorts and a tank top. I'll turn on my AC. What's the big deal? This increased temperature is going to destroy modern ecosystems. How? By changing weather patterns. And the weather patterns are changing faster than the populations can evolve. And when organisms cannot have their gene pool change faster than the conditions, eventually they are so unfit that the population goes extinct. We're going to have mass extinction events. Now, don't get too bogged down by this. We can do something about this. We need to talk about it. We need to figure out what we're going to do about our fuel source. Okay, it's very easy to say, stop burning coal. Right, go to Pennsylvania and tell the coal industry that we're going to shut them down. So if you go to Pennsylvania or Indiana and you start shutting down their fossil fuel industry, what are you going to do for the workers? How are you going to retrain them? There are politics and economics that we need to discuss with the science, right? So don't let this bog you down. Figure out what we're going to do about it. We need to change our fuel source. We need to change our habits of consuming resources. And we need to figure out how we're going to help the people that we're shutting down their industry. All right, question 4B. 4B, it says global temperatures and climate patterns are influenced by concentrations of greenhouse gases. That's what we just talked about. There's a correlation between rising atmospheric concentrations of CO2 since the start of the Industrial Revolution, right? We're burning fossil fuels to power that industry. Let's see, recent increases in atmospheric carbon dioxide are largely due to increases in the combustion of fossilized organic matter or fossil fuels. Okay, so it dropped a term there. So this is question 4B. It dropped the term correlation. Now, even though we say correlation, if you really look at it, that's correlation. That is a relationship with. You go, a relationship with what? With each other. That means that there is a cause-effect relationship. Okay? We have the burning of fossil fuels, that's our cause. What's the effect? Increasing global temperature, changing weather patterns. You change temperature, you change precipitation, you've changed climate. Thus, global climate change. So, here's a gentleman that I need you to look up on Google. Good old Charles David Keeling. Now, unfortunately, Dr. Keeling is not with us anymore, okay? But he worked at a place called Scripps Research Institute. Now, Scripps Research Institute, or what we commonly refer to it as SIO, there are two leading oceanographic and marine biological research facilities in the world. One is Woods Hole in Rhode Island on the east coast of the US, and the other one is Scripps Research Institute in, guess what? La Jolla, California. Okay, so understand that up in La Jolla are three things. In La Jolla, there's UCSD, there's the Salk Institute, the #1 research institute of basic science in the world, and literally right across the street is Scripps, is SIO. Those three are all located right here in San Diego. We live in the mecca of science. It's amazing. So, in about 1958, Dr. Keeling, up in La Jolla, started thinking about the burning of fossil fuels and the release of CO2 into the atmosphere. And so he started tracking CO2 concentration all the way up to his death in 2005, right? And it's a simple curve. He put time down here and CO2 concentration here. Okay. Now, eventually, he started collecting this data in Hawaii, all right? Because people criticized his data collection in San Diego, claiming that it was contaminated by all of our naval and shipyards and our industry in San Diego. So he said, all right. And so he went out in the middle of the Pacific Ocean, one of the small islands close to Hawaii, where there's no industry, and collected the same data. But he started and did all of his writing up in La Jolla, right? And so what you're going to see is you're going to see a graph that looks like this. So go on the web and look this up. And we refer to this as the Keeling Curve, all right? And it's from the late 1950s. And most of them will stop about 2005, especially if it's labeled the Keeling Curve, because they stop at around 2005 in acknowledgement of his death. But of course, they're still collecting this data. This graph continues today. And so what it shows over almost 60 years is this gradual increase of carbon dioxide concentration over time. But you'll notice there's this really nice rhythm to it where the CO2 bounces up and down. This is where people say, oh, CO2 concentrations bounce up and down all the time. This is nothing new. Okay, the general slope of this line, as you see, is positive. I agree there's undulations up and down. You say, well, why? Well, here's what's cool. In the springtime, you have a lot of plant growth. And in the spring, if you have a lot of plant growth, then the plants are doing photosynthesis. When plants do photosynthesis, what gas do they take in? They take in CO2 for photosynthesis. As all of the plants are doing tremendous amounts of photosynthesis in the northern hemisphere, right? There is a reduction in CO2 as the plants start sucking some of it out of the atmosphere. That's the dip. So it's spring, 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 spring. Well, then hold it. What's with the increase? What's the increase from? That would be fall. In the fall, deciduous plants dump their leaves, and then the saprotrophs, the decomposers, then break those macromolecules down and release CO2. So what this really is, the drop, spring, increase, fall, drop, spring, increase, fall, and spring, and fall, and spring, and fall. And so there's this really nice rhythm back and forth, and you'll see that this rhythm occurs twice every calendar year as the plants are either growing or dropping their leaves. But this is called the Keeling Curve. This is a classic curve. You need to be comfortable with this. Whether you draw this out in your core or you print it and glue it in or tape it in, totally up to you. There's a second graph that I need you to look up, and that's the geological graph, okay? We're going to keep the same x-axis, the same y-axis. We're going to keep carbon dioxide concentration here. We're going to keep time here, but we're going to change our scale. Make this 800,000 or 1,000,000 years ago. It depends on what you look up on Google, okay? Make this somewhere between 800,000 and 1,000,000 years ago. And then make this today, all right? And here's what you'll see. There'll be a cycle somewhere between about 250 and about 300 parts per million. Okay, so if that's 250, that'll be 350. So let me take this up to 4, and you'll see why in just 1 second. You're going to see a cycle here between 250, 300-ish. You're going to see this over about the last 1,000,000 years. How do we know this? Ice core samples. We actually have the atmospheric sample. And then what you'll see is, boom, I guess it makes a little sound effect, between 1800 and 1900, and then today, you will see this dramatic jump, and we have unfortunately surpassed 400 parts per million. These are parts per million of CO2, all right? So this is the other statement where people will say, oh, global warming isn't real. We have nothing to worry about because after all, and what they'll do is they'll show you this graph. And they'll say, look, over the last 1,000,000 years, the CO2 concentration has bounced up and down. It is a very natural, normal process. Nature cycles CO2. And when you see this graph, say, excellent, show me the end of it. When people present this graph as being critical of the Keeling Curve and critical of global climate change, they always trim this end off because they want you to see this data. And you say, show me all the way up to today. Show me the industrial spike. And now explain where this came from. This is due to volcanic activity. This is due to off-gassing by the Earth. These processes are still happening. I haven't noticed in the last 100 years this incredible increase in volcanic activity, right? So where is all this CO2 coming from? It's coming from the fuel that we burn. Okay, so that's question 4A and 4B. This should wrap up core 4, and then I will start core 5 here in the next week or so. And don't feel any pressure to get core 5 done immediately. I mean, if you want to dig in, and we need to have core 5 done by August, right? So this is core 4. Talk to you guys soon.